Our next speaker is Mario Bergeron of Avnet. Mario is a technical marketing engineer for Avnet Electronics Marketing, specializing in video, image, and digital signal processing. He earned his BS degree from Laval University in Quebec and started his career as an ASIC designer. And I've had the privilege of working with Mario on multiple projects, and for that reason, specifically recruited him to come talk here. He wasn't planning on doing it. He was a little hesitant at first because he didn't realize just how much he knew until I pointed it out to him. And then he readily agreed to put together a presentation and share some of these insights. You know, there's been a lot of talk here about the software and about the processors, which is both critical. And we're going to talk about the sensors, which are also critical. But there's also the putting it all together part, which is equally critical, but not quite so easy to put your finger on, and so frequently overlooked and really at your peril overlooked. So that's what I asked Mario to focus on, is the putting it all together aspects. Mario?
All right. Thanks, Jeff, for that nice intro. So as you mentioned, I'm Mario Bergeron with Avnet Electronics Marketing. So one of the things that we do is create development kits and reference designs and marketing campaigns around the great technology that manufacturers are making. With Avnet, we try to bring the solutions from different manufacturers together as system solutions when we can. So I've been involved in co-processing platforms and video stuff, so I'd like to share some insight that I've gathered from that. So hopefully you'll find this useful. So from today's presentation, it should be pretty clear that there is quite a large landscape of embedded vision solutions, hardware-wise. There's two ideal points to be in, I think. In the low end, if you're working with small frame sizes and small frame rates, good for you. That's perfect, because there's a lot of technology available to you at very low cost, very low power. This is an ideal spot to be in, right? The low end. Another ideal spot could be if you've got very high performance requirements, but you have absolutely no limit on cost or power. Well, then go for it. There's tons of manufacturers. Like, you build up a rack, just pop those processing cards in, and you're on your way. But there's a good chance, like most of our customers, that you're somewhere in between there, right? Which we'll call the challenge zone. So you need moderate to high performance, right? These are, you're working with non-trivial frame sizes or frame rates, yet you've got the constraint of moderate to low cost and power. So in this session, I'm going to try to address this, but from the angle of moving data around in your system. Because ultimately, moving data around will define the cost and even size of your system, and is often the critical bottleneck in your system. So that's the angle I'm going to take for this presentation. So the case that I've decided to do, we've got a lot of requests from our global regions to create a development kit with image sensors with higher performance than what's usually available, yet to add the capability of analyzing the video content. So the basic recipes of creating an embedded vision system, if you want. So we've chosen this image sensor family from ON Semiconductor. It's an interesting image sensor because it's somewhere between the surveillance and machine vision application spaces, yet at a reasonable cost. So the table lists the devices in this family. So you can see this lower end has about 1K by 1K, can go up to 150 frames per second still. But the higher device has a 5K by 5K active area. And as you can see, each of these devices has a constant maximum throughput if you want, right? So with the maximum image size, there's a frame rate associated with it. And that corresponds to a throughput. And the throughput is basically your image size times your frame rate. Pretty simple formula. But you're free to program the image sensor to your needs. So as I pointed out in this example, the VA2000, if you don't need this big of a frame size, you could use a smaller image, just crop down your image, and you get the same bandwidth, so you can increase your frame rate. So ultimately, this image sensor family is kind of what our customers were looking for, kind of in this range. But if you look at these throughputs, these are bits per second, so 2.5 gigabits per second, up to 20 gigabits per second. That's a lot of bandwidth. And these are 10-bit pixels on this image sensor, so that corresponds to, for these two guys, 250 megapixels per second of pumping data. And for the bigger device, 2 gigapixels per second of data. So, all right, we've selected this might be a little more higher end than what you're looking for, but I'll carry through the example, and hopefully you'll get some just insight on what's involved in moving all this data around. So we've got our image sensor. How do we get the data out of the image sensor? Well, one of the first challenges that you may run into is the interface to the image sensor. Using traditional parallel interfaces, we've already hit the limit of what this interface can do. As an example, the ON semiconductor has 2 of the smaller devices available with parallel interfaces, but when you use this interface, only 25% of the bandwidth is available. Why? Because the interface it's clogged, right? It's not able to pump that data out. So parallel interfaces is basically you take your pixel width, which I talked about is 10 bits, and you have a pin for each of those bits, right? So here we're talking about a 10-bit interface with some synchronization and a clock, and this will usually top out about 100 megahertz per pin. So what you'll usually see is although image sensors with a parallel interface can get you to high-def image size, they'll usually stop at 30 frames per second. So the solution to this, and we're starting to see this pretty much everywhere, some image sensors have both flavors, so you can choose which one you want depending on your needs. But to go to higher frame rates, especially for high-def video at 60 frames per second or more, you will see serial interfaces. So the idea here is you take your 10-bit parallel path and you transmit it 10 times faster on one pin. So you've saved the number of pins. And this uses low voltage differential signaling. So you've saved power. These interfaces use less power. And obviously these LVDS pairs can go up quite higher, 1 gigabits per second per pair or more. And the way that ON Semiconductor has implemented this in the image sensors that we're seeing is they didn't choose to pump the whole 10-bit data in one channel. They split it out into 4 channels. So it actually makes an interesting data rate for very low-cost FPGAs, as we'll see in the next slide. And the way that they scale this out to the different devices in the family, they just add different parallel paths. So for the larger device, there's 8 times more parallel paths to get that 8 times more bandwidth. So now, how do we receive this data from the image sensor? We talked about using serial interfaces for higher performance image sensors. Unfortunately, serial interfaces can be proprietary. Standards are starting to appear. The mobile market is pushing MIPI or MIPI. So that's interesting there, but not everyone is adopting that yet. As in the case for OnSemi, it's a proprietary LVDS-based interface. And there's a good chance that these interfaces are not available on standard processors and or DSPs. So the solution that we went with is to take FPGA technology. FPGA can easily deserialize these serial interfaces in the fabric. And the fact that FPGAs are inherently parallel processing in nature, so it scales very well to the image sensor family that we've selected here, right? So for the Vita 2000, each data channel is pumping 62 megapixels per second. That's actually pretty low. So you can get a very low-cost FPGA to do that very easily. And for your 25K, the 5K by 5K image sensor, well, you just got more data channels. So if your processing could be mapped out with parallel data paths, then this very high-performance image sensor family scales very well to FPGA technology. So another challenge, as many presenters have mentioned, is video storage. So obviously, you've got to have video processing in your system. These require storage. I have 3 examples just to show if there are people in the room that are new to video or vision, just how the storage relates to the algorithms. So the very simplest processing I like to consider is pixel-based processing. You don't need storage for this. You could store between the processing stages, but you don't really need it because for every pixel coming in, you process and send it out. There's no intermediate storage needed, apart from maybe some parameters. That's the simplest one. Then there is the spatial processing, which is using a neighborhood of pixels to generate one output. So in this case, pixels are usually flowing in the system one by one, line by line. So the way that you would do this, you need to store previous lines of video before being able to generate that output. So this is usually implemented with line buffers, right? So you need storage the size of the line width. So pixel processing might be things like color correction, gamma correction, right? pixel in, pixel out, whereas spatial processing would be like these edge detectors we've heard about. Even defect pixel correction would be using this, because if you identify a defect pixel, you need to look at its neighbors to put in what would be a most probable correct value for that pixel. So there's a lot of examples of these spatial processing. And the most hefty one is any kind of temporal processing where you need pixels from a previous frame to do your calculation. Well, then obviously you need to store the entire frame. So that's a lot more storage requirements, and that's where you start to see frame buffers in your system. So the memory requirements imposed by your processing, by your algorithm, so the size of the memory will depend on the image size and how much frames you need to store, how much history, how far you need to go in the past. And in terms of bandwidth, that also depends on image size times frame rate, as we mentioned, but also how many times you're going to dip into that frame of memory, right? It's not true that a complex algorithm is going to just read the frame of memory once and have an output. You're probably going to need to go back and forth into it a few times. So that's really dependent on the algorithm. So how does this map out to memories? Well, memory is typically available in the most common types of memories that we see is we'll have SRAM-based memories on chip. They're smaller. Unfortunately, they're not big enough to hold a high-def image, but they have very high performance. Whether you read your image or subset of image in order or out of order randomly, they'll always have the same performance. So that's good. That's the ideal place to be. And that's why if you're working with very small frames that fit into this on-chip SRAM, that's the ideal scenario. There's also off-chip memory, which is DRAM. These are larger capacity, so you can implement some frame buffers. And here what I've called higher latency in the sense that if you read your frame in order, row by row, you'll get very good performance out of that memory. But if you start reading pixels randomly, if your algorithm requires this, then your performance on that memory is just going to drop to the floor, like maybe 10% or less. That's just the way that the memory works, right? Every time you change a page, you have a page, you have to reload, you have to change that page. That's the way that the memory works. So how is this memory used in the systems? Well, DRAM memories obviously are going to be used for the frame buffers. So I've added one here. The SRAM will be used for line buffers, parameters, and even for processors, they can be used as a cache to accelerate the performance of that external memory. In FPGA, interestingly enough, the on-chip memory is implemented as block RAM. So it's little chunks of memory, and conveniently, the size of memories are about half the size of a line of video. So that's just convenient for video because you can implement a line buffer using a few of these block RAMs without wasting them, and they become localized to that processing unit. So that's almost an ideal, in my opinion, use of that on-chip memory on the FPGA for video. And if you don't have enough horsepower for this external DRAM on an FPGA, well, as long as you don't run out of resources and pins, you can just pop them on as your application needs. So it's very scalable and flexible in terms of memory in FPGA. So now I build up a system with an FPGA. Recall that we're creating an embedded vision, right? Embedded vision, we've had presentations all day. The challenges of that are, obviously we have a lot of compute-intensive tasks, very high pixel rates, yet we need to perform video analytics, complex decision-making, maybe even add some networking, graphical user interfaces to the system. So how do we map that out? Implementing all this on an FPGA I don't think would be feasible, technically possible maybe, but might take you, by the time you implement everything, your window of opportunity may have just slipped by. So what do we do about that? You may need to leverage existing libraries. There's been a lot of talk about OpenCV, proprietary algorithms, and legacy code that you may already have. So in my opinion, a very viable solution is to pair up an FPGA with a processor or DSP, or both. And so you keep your FPGA. We saw that we used it for the serial interface to the image sensor. Why not use it to do that, all that compute-intensive task on that high bandwidth of video, and add the CPU in your system for the more complex decision-making, the intelligence of your system. You may even want to add some feature detection in that FPGA to bring your bandwidths down before passing that up to the processor. So This is a very viable solution. It's what I would call a co-processing platform. We've built a few of these at Avnet based on DSPs and on processors. And everything works really fine when you have, got this on the next slide. If your FPGA is just used for pre-processing and you're just passing the result back to the processor or DSP, this architecture works really nicely. But if you start to want to go back, bring data back and forth between the FPGA and the processor, reusing that same FPGA for co-processing to accelerate things that are happening in the CPU, well then, obviously this guy, right, it's all about data movement. This is going to become your bottleneck, unfortunately. And we've seen this with some of our co-processing platforms. So what's the solution to this? There's been a few mentioned that it would be nice if we have people integrating all these pieces together. Well, that is happening. That is starting. We heard ADI mention about their DSP where they're combining a CPU with a DSP and some, not an FPGA, but some programmable hardware accelerations. So that's one example. Another example was mentioned by Xilinx where they've combined 2 ARM cores with FPGA technology. That's actually the one that we chose for this kit. So the Xilinx Zinc 7000 SoC combines the dual-core ARM with FPGA technology. And this is what the final system looks like that we have running on our booth. What's important to note here is that these 2 technologies are in the same device. The blue here is the dual-core ARM system with dedicated peripherals. The yellow section is the FPGA, if you want, inside that device. But one point I really want to stress out is these are very tightly interconnected together. There's a lot of bandwidth available here between the 2. There's 4 high-performance ports that can go up to 10 gigabits per second each. So very interesting. This whole, we have an example. We don't have any intelligence running on the reference design that we're showing at the table, but it shows how you can get this high bandwidth video going through the system. And these ARM cores have the neon accelerators, and they also have an accelerator coherency port, so you can do some co-processing inside this fabric. And so very flexible architecture, in my opinion, you should really check out if you're doing embedded vision. At least consider it. So I think I'm pretty close to the end. So just to summarize, I've touched on image sensor interfaces and how to get higher performance image sensors, you'll need to go to serial interfaces, so you need to consider that. And I've mentioned FPGA technology and how it offers a very flexible and easy interface to those serial interfaces, but also how it can be used for programmable high-performance video processing, and how it's got very flexible memory solutions. You determine exactly the memory that you need in your system. And we've also seen that there's starting to be highly integrated devices, in this case the Zinc 7000 SoC, which combines industry standard processors with FPGA technology. So that's the end of my talk. Thank you very much.
Thank you very much.